So, welcome back. Let's solve the second example with the same concepts what we discussed earlier. So, example 2. So, consider a fixed wing UAV with a wing and tail plan form with a rectangular wing and tail plan form area, rectangular wing and tail plan forms with an area ratio of 0.25, which weighs about 550 kg. Okay, and cruising at sea level. So, with the following data, find A. So, find the neutral point or the location of neutral point. I say NP, right, neutral point. B, so total lift curve slope of UAV. Okay, so total lift curve slope of UAV. Static margin location of CG with respect to leading edge. Leading edge of wing. Horizontal tail volume ratio and tail setting angle. So, horizontal tail volume ratio. So, with the stability analysis, we are trying to fix the geometric parameters. What should be the wing planform area? What should be their location? What should be the tail volume ratios? So, that's the main aim here. Horizontal tail setting as well as horizontal tail setting angle. Zero lift angle or zero angle of attack lift coefficient of UAV. Right. So, we are asked to find out zero angle of attack lift coefficient of UA. So this is what we need to find out with the given data. So let's now look at what is the given data here. So CL alpha of wing is given as 5.056 per radian. So CL alpha of tail is given as 3.38 per radian. Alpha at which CL is 0 is minus 2 degrees. C bar is 1.2 meters and the span is 10.5 meters. Cm naught of the UAV is 0.0928. Right. So in our previous example, we figured out what is Cm naught, but right now we are trying to find all these parameters, assuming this particular Cm naught is given. Okay, so that's the difference. So Cm alpha is minus 1.0163 1623 per radian, 0.016. That's good enough. Tail efficiency factor eta of t is 0.89, which is 90% approximately, and then XAC of the wing is 30.32 meters behind the leading edge. So XAC of wing 0.32 meters behind the leading edge, and XAC of tail is 2.95 meters, 925 meters, 2.93 meters approximately behind the leading edge of the wing. And we are also given the data about epsilon downwash is equals to 0.75 degree plus 0.375 times alpha. Okay. So that means first thing that I would like to do is epsilon naught is 0.75 degrees. I need to convert to radians, which is approximately 0.013. So 0.013 radians, right? So dou epsilon by dou alpha, it is same whether, because radian degree upon degree or radian upon radian, right? So it will have an increment in a similar way over when you consider epsilon as a degree or epsilon as, yeah, so same, you need to have similar units here and there. So this is the data. First of all, location of neutral point. So before finding out the location of neutral point, I would like to address this second question. So question B, I am trying to address it first. Total lift curve slope, right? Total lift curve slope CL alpha of the aircraft is, as we know, it's from the contribution, wing contribution, and with a correction factor from the tail, as well as from the tail contribution with a correction factor here, St upon S times CL alpha of tail 1 minus dou epsilon upon dou alpha. Straightforward, right? Just substitute the values here. The CL alpha of the total aircraft is, what is CL alpha of wing, which is given as 5.056. We can say 5.06 or 56 plus eta is 0.89, 89%, and St upon S is given by 0.25. So the wing area ratio is 0.25 St upon S. From the given data, what we have is, since St upon S is 0.25, and we were told that these are rectangular wings, right? Isn't it? Multiplied by CL alpha of tail is 3.38. CL alpha of tail is 3.38. 1 minus dou epsilon by dou alpha is point. So from here, you know, dou epsilon by dou alpha is 0.375, 0.375. So CL alpha contribution from wing is 0.056 plus tail with the correction factor we have 0.47, right? So CL alpha of the entire aircraft, this implies CL alpha of the entire aircraft is 5.526 per radian. Okay? Simple, straightforward question. No complexity. Now let us address this first question. What should be the location of neutral point? Now you can appreciate this, right? So how less the contribution from the tail towards CL alpha. That's because that majorly affected by this ST upon S. If this is 1, then it is almost close to 0.89 is like 90% of this, and without downwash it is almost same, right? Isn't it? So, but because of this ST upon S, which in fact you decide based upon the required tail volume ratio. Right? So, due to which your contribution of CL alpha tail towards the CL alpha aircraft is very small here. Right? And the location of neutral point here, so location of neutral point, right? Okay, so location of neutral point NP. Okay, so how can I find out? I don't have the data about CG here, right? Or say if I have static margin, then I will be able to find it out directly by adding static margin with the CG. But I neither have CG data or the static margin data. All I have is the location of wing, location of aerodynamic center of the tail, and then so I have the corresponding lift curve slopes of wing and tail, right? Am I correct? And I know what is the area ratio of wing and tail, which is 0.25. So with this data, I will be able to figure out neutral point, right? Weighted average. I use that weighted average formula, which is x bar np is equals to CL alpha of wing times x bar AC of wing plus CL alpha of tail, okay, with correction factor, eta of tail ST upon S times CL alpha of tail times 1 minus dou epsilon by dou alpha is the correction factor due to downwash multiplied by the location of aerodynamic center of tail with respect to the leading edge of the wing upon CL alpha of wing plus eta ST upon S times CL alpha of tail times 1 minus dou epsilon by dou alpha. Yeah. Okay. So can I say this is my total CL alpha of the UAV? So this particular denominator is nothing but the total CL alpha of my UAV, right? Am I correct or not? So I can directly substitute the value that I obtained here in the denominator. Okay. So what I will do is x bar np is equals to CL alpha of wing upon total CL alpha of the UAV multiplied by x bar, its location, corresponding location. So this is the weight to the location, right, to the location of aerodynamic center of wing plus eta ST upon S CL alpha of tail 1 minus dou epsilon by dou alpha. So this is divided by CL, total CL alpha of the aircraft, right? So again, this is the weightage to x bar AC of tail, which is its location. Okay. So x bar np is equals to, this equals to 5.056 CL alpha, 5.056 divided by CL alpha is 5.526 multiplied by XAC, location of aerodynamic center is 0.32, right? So 0.32 upon c bar. C bar is given as 1.2 meters, right? So this is 1.2 meters plus point. So this is approximately 0.47, right? Isn't it? So 0.47 upon CL alpha is 5.526 multiplied by x bar AC of tail, which is again given by 2.95 meters upon 1.2 meters. 2.925 upon 1.2 meters. Okay. So from here, I know what is x bar NP, neutral point, which is equals to 0.914 times 0.267 plus 0.085 times 2.438. Okay. So what do you mean by that? So this particular ratio is the weight to the location, right? Is the ratio of lift curve slopes, no, of the wing to the entire aircraft. Am I correct or not? And lift curve slope of the tail to the entire aircraft. Lift curve slope of the entire. So it is getting like the wing is having the major weight here. No, that's why XNP tries to have a major weight, almost 1 towards its location, wing aerodynamic center location. That means this particular term will try to pull the aerodynamic center towards it because it has a more weight. No? Yeah. So, but the location, see here you have only, here it is 91%, no? Almost, it's almost 1 here, right? 100%. It will try to pull, the wing try to pull the neutral point towards it because of this. But here you see it's only about 9%, which is 8.5%, but the length of the tail is what matters here right now. Yeah? The location of aerodynamic center of the tail is what making this to pull towards that, pull towards the tail. So the neutral point is now because of the weight to the location of the wing CG and the weight of lift curve slope towards the location of wing aerodynamic center here. Okay. So what it turns out to be somewhere in between these two locations, right? X bar NP is 0.451. Can you see this? No. X bar NP is 0.451. If you multiply by C bar, what is the value? Corresponding location is X NP is equals to 0.451 times 1.2. How much? 0.541 meters from the leading edge of the wing. You see this is aerodynamic center of the wing is 0.3 meters. So shall we draw this? That will make sense, right? Isn't it? Yeah. Say if this is my fuselage reference line, okay. Let us say this is my reference point or leading edge of the wing, okay. So the wing is located at a distance. So wing AC, aerodynamic center of the wing, let us say, is located at a distance here. So let us say this is my AC of wing, which is at a distance of 0.32 meters, right? This is 0.32 meters. And the CG, or say the tail is now located at a distance very far from here, which is about 2.93 meters, 2.93 meters. Look at that. This is just 30 centimeters. That is 292 centimeters from the leading edge. So this is far away. This is AC of tail, which is located at 2.93 meters approximately. Okay. Right. So this is XAC of tail, and the neutral point turned out to be at somewhere here. See, approximately half a meter. So this is your neutral point, which is 0.54, approximately 54 centimeters, half a meter. So this is your NP. No. That means your CG for a stable aircraft has to lie ahead of NP. That is what we discussed. NP makes the system, if the CG is beyond this NP, it's a limit for CG, beyond which it becomes unstable, Cm alpha becomes positive. So before that, that's the same case. For the wing alone, we saw the wing starts flipping back. As soon as the CG shifted back the aerodynamic center, which is the neutral point for a wing alone configuration, it starts flipping back immediately. Right? So the CG has to lie close to this aerodynamic center itself, towards this point. Am I correct or not? And see the strength of this CL alpha of the wing contribution. So it is pulling this towards it. Although the tail have a greater moment arm, which is about 2.95 meters with respect to leading edge of wing. So, but it has only a smaller moment arm. But the domination is from the wing contribution, wing area, isn't it? ST upon S of wing upon S is 1. But here S of wing upon S of tail upon S is 0.25, 1/4 of it. So this is what is like making the contribution of CL alpha of the tail very less towards the neutral point comparatively. Am I correct? So that is what is happening here. So we figured out neutral point and the total lift curve. Let us talk about this static margin. So let's talk about solution for this third question. Third part of this question, which is find out the static margin with this current CG location. Okay, how to find out static margin with the current CG location. Find the static margin. SM. So static margin is equals to minus d upon dCl. Do we know that? Which is equals to minus Cm alpha upon CL alpha of the total aircraft. And CL alpha of the entire aircraft is known. It's easy to find out static margin, right? So Cm alpha is minus 1.01632. That's such a long number. Minus 1.0163623 upon CL alpha of the entire aircraft is about 6, if I'm not wrong. 5.526. Okay, 5.526 per radian. So the static margin turns out to be 0.184, which is approximately 18.5% or 18% I should say. Okay. So approximately 18% is the static margin of this configuration with this current CG location. Okay. So let's move ahead to find out what is D, right? What is the D? Location of CG. Now location of center of gravity with respect to leading edge of wing. What do you mean by that? So I need to find out. So we know what is NP. You now know the static margin as well. You find what is the location of the CG. Okay. So say somewhere here, say this is my CG location and this is my XCG. Okay. You know by the definition of static margin, we have x bar NP minus x bar CG, right? This implies x bar CG or XCG is equals to XNP minus static margin times C bar. Okay. So since we want a dimensional quantity with respect to the leading edge, so I'm trying to multiply that C bar for this entire equation. So XCG is x bar XNP, which is 0.54 meters, 54 centimeters from the leading edge of the wing, minus static margin is 18%, right? So See 0.184 times C bar is 1.2 meters. So 18% of 0.2 or close to 20, it is like, yeah, 20% of 1.2 meters. So this is equivalent to 0.32 meters. 3 to 4, and the CG and the AC are almost same. So very close. Yeah. So very close. CG and the aerodynamic center of the wing are very close here, almost close. If you have to have 20% static margin, almost close to 20%, then the CG of the UAV is almost close to the aerodynamic center of the wing here. Right? That means there will be a very weak contribution of CL of the wing towards CL naught of the wing towards CMAC or CM naught, sorry, CM naught of the aircraft. Okay. So let's go ahead and solve this problem. Horizontal tail volume ratio. So what is horizontal tail volume ratio? So DE is a, we need to solve for horizontal tail volume ratio. So we know VH, right? ST upon S times X bar XAC of tail, or LT upon C bar, which is ST upon S. LT is given, otherwise you can say ST upon S. LT is XAC of tail minus XCG upon C bar. So straightforward. Please substitute this, and then this is 25%, 1/4 of the wing times. So this is 2.438 minus 0.267. So this turns out to be tail volume ratio as 0.542. Right? So this is a very good number, very good tail volume ratio, 0.542. And the next question is about finding out the tail setting angle. Right? So find the tail setting angle. How do you find this tail setting angle? You have CM naught given, right? You know CM naught. We know tail setting appears in CM naught, right? Affects the CM naught. So let us write down that equation. CM naught is equals to CM AC of wing plus CL naught of wing times X bar CG minus X bar AC of wing minus eta ST upon S CL alpha of tail 1 minus dou epsilon, sorry, I of t minus epsilon naught multiplied by, or you can directly say VH, tail volume ratio. I am writing in terms of VH here. Right? Since we have already calculated what is VH, I'm just substituting that there. So I of t plus epsilon, right? Isn't it? Or minus epsilon? Minus epsilon, yeah, true. So I of t minus epsilon naught. Epsilon naught is 0 for this or not? Yeah. So from here I can say IT plus, IT is equals to epsilon naught plus, right? IT is equals to epsilon naught plus 1 upon eta tail volume ratio CL alpha of tail, okay, multiplied by CM AC of wing plus CL naught of wing times X bar CG minus X bar AC of wing minus of CM naught of the entire aircraft. Isn't it? Okay. So from the given data, you can substitute this and figure out that value. What should be the I of t? So consider a rectangular symmetric wing and tail. It should be a symmetric. Rectangular symmetric wing and tail. Okay. So please add this part here. Consider a rectangular symmetric wing and tail, which makes CMAC is 0 and CL0 is of the wing is 0. Right. So what you end up having is epsilon naught, which is I of t is 0.75 was given, right? 0.013 plus 1 upon 0.89 times tail volume ratio is 0.542 multiplied by CL alpha of tail, which is 3.38. So this is equals to 0 plus 0 minus 0.0928. Okay. So what do you end up having is, so I of t is equals to 0.013 minus 0.0568. Right. So what is the value? IT is minus 0.0439, which is approximately how many degrees? This is in radians. So this is minus 2.5 degree. Okay. So this is a tail setting angle you need to maintain in order to have this Cm naught, right? This is the Cm naught. In order to have this Cm naught positive, you need to maintain this particular tail setting angle, right, which is minus 2.5 degrees. So let's move on to the next question. Zero angle of attack lift coefficient, right? So you need to find CL naught of UAV. So it's straightforward, isn't it? CL naught of UAV is equals to CL naught of wing times XCG minus XAC bar of wing plus eta st upon s times CL alpha of tail times I of t minus epsilon naught. Okay. So but CL naught of wing is 0, isn't it? Oh, I'm sorry. Okay. So please make this correction. Just trying to write about Cm naught. No, this is CL naught of wing plus eta st upon s, CL alpha of tail, I of t minus epsilon naught. So CL naught of wing is 0 because we have a symmetric wing and tail, right? We have symmetric wing and tail, because of which CL naught of wing is 0. So the CL naught of the total aircraft is from this tail contribution. Okay. So which is minus 2.5 degrees, right? Which is approximately minus 0.0439 minus 0.013. Right? So eta is 89% and 0.25 is st upon s. This is 3.38. 3.38 is the lift curve slope of tail multiplied by minus 0.069, right? Minus 0.043 minus 0.013. Yeah. So minus 0.056, right? So this equals to, so if you multiply all of this, what are you going to get? So CL naught is equals to, so the CL naught that I am going to have because of this is how much? Minus 0.042. So this is the negative CL naught contribution because of the tail setting, negative tail. So when Wing is symmetric, so at 0 angle of attack you have negative lift. Okay. If you have a minus 2 degrees tail setting angle, so you may not be able to fly at 0 angle of attack. Of course, we have a symmetric wing there. So you need to trim always at certain positive angle of attack there, right? Or employ a wing setting angle, right? Continuous wing setting angle. When you consider a symmetric airfoil for the wing, then you have to maintain a continuous wing setting angle. Okay. And let's take up the final question. So it's altogether a performance question kind of, no? So find the trim angle of attack. Find the trim angle of attack and the corresponding lift and drag forces as well as power required for the UAV to cruise at sea level. Okay. So assume CD naught is 0 lift, drag coefficient is 0.03 and Ostwald's efficiency factor of 0.9. Okay. So we need to figure out first the trim angle of attack from the given data for the same UAV. Again, we know we'll go back to the Cm versus alpha for trim angle of attack, right? So we have Cm naught. We know Cm naught. What is the Cm naught value for this aircraft? 0.09. It's given 0.0928. So the coordinates at this point is 0, 0.0928. Yeah. And we know alpha trim here, so this corresponds to alpha trim, 0. At trim angle of attack, the moment coefficient is 0. Am I correct? Okay. So I know the slope here, dCm upon d alpha. Cm alpha is known. What is the slope? Minus 1.01632. Minus 1.01623. Yeah. Per radian. Okay. So by using the definition of slope, I will simply calculate what is the corresponding trim angle of attack here, right? So alpha trim is equals to Cm naught upon minus of Cm naught upon Cm alpha, isn't it? So what is alpha trim? Cm naught is 0.0928 upon Cm alpha is minus 1.01623. This is equals to 0.094 radians. So this implies alpha trim is approximately 5.4 degrees. Okay. So this is the trim angle of attack, no? 5.4 degrees. I was able to find out that value. So I have this trim angle of attack. And with this data, can I be able to find out what is the lift and drag coefficient? What do I require to find out those? So first of all, lift is half rho v square s times CL, isn't it? This is half rho v square s times CL, and we need to know what is the cruise velocity as well as CL here, because density at sea level is 1.225 kg upon meter cube, and we have wing area because B is given and C is given, right? So I know S is B times C bar. C bar is nothing but so C throughout. No, it's a rectangular wing, so C bar doesn't make any sense. It is nothing but root chord, tip chord, everything. At a given cross section, this will be the corresponding root chord length. So for a rectangular wing, this is B times C bar, which is nothing but B times C. So this is 10.5 multiplied by 1.2, which is 12.6 meter square. Okay, 12.6 meter square. And then we have the area. Now we need to find out CL, right? This CL is CL of the total aircraft, isn't it? CL of the total aircraft corresponding to alpha 3 degrees, 5.4 degrees trim. Am I correct or not? So I can express this CL as of the total aircraft as CL naught of the total aircraft times CL alpha of the total aircraft times alpha trim, right? So this is CL trim. So this is equals to CL naught of the total aircraft. We have calculated it as minus 0.05. How much is that? CL naught of the aircraft? Minus 0.042. Right? Plus CL alpha of the total aircraft is 5.526, right? Multiplied by 0.94. It is in radians, no? This is in radians. So let's continue working in radians. Alpha trim in radians is 0.094. So what is the value? Zero point 477. So CL trim is 0.477. So if you substitute CL trim there, you will be able to find out the lift. But we don't know what is the corresponding velocity. Right? So since we are cruising at sea level, during cruise, we know lift is equals to weight of the configuration. This implies half rho S times CL trim is equals to W. This implies V for CL trim or V trim, corresponding V trim is equals to root over 2W or twice the wing loading upon rho CL for trim. So this equals to Prabhjit, 2 times W 550. So 550 kgs it was given. So we need to convert it to newtons. I am considering G as 10 meters per second square. So this is 5,500 newtons upon 1.225 since we are flying at sea level. So density at sea level is 1.225 kg upon meter cube times CL trim. So CL trim what we have is 0.477. So quickly calculate the value of V trim. V trim is equals to 38.65. So close to 40 meters per, so 39 meters per second, right? Close to 39. So if you substitute V trim in this particular equation, what I have is half 1.225 times 38.65 square. Okay, half rho V square times the area, which is 12.7, 12 point, we just calculated it, 12.6 times 0.477. What is the value? The lift force acting is, what should be the value? Without even calculating that we should say, isn't it? It should be 550 kg or 5,500 newtons, close to that, maybe 5,493 or something. How much is that? 5,500 newtons, which is 50 kg. We need to calculate that because we are in cruise. Lift should be equal to weight. There is no need to calculate that lift is equals to weight there. You can directly say it. And what is the drag? So drag is equals to again half rho V square S times CD naught from the drag polar equation times KCl square. So you substitute the value of CL here, you are given CD naught and find out what is. So if you do that, what you are going to have is 0.5 times 1.225 times the reference area here is 12.6, half rho S V square is 38.65 square, okay, half rho V square times CD naught is 0.03 plus K we need to find out, right, isn't it? K, we don't have the value of K. K is equals to 1 upon pi E AR, right? So 1 upon 3.14 times what is E? Consider, so E is considered as 0.9, sorry, 90% efficient. And then the aspect ratio is B square upon S or B by C directly. So B is 10.5, C is 1.2, B by C is approximately 8.75. 8.75. So the value of K turns out to be 0.04. 04, right? 0.0. So 0.04 multiplied by CL square is 0.5 approximately, or 0.477 square, right? So if you solve this, the drag required is approximately 454 newtons or K, yeah, 454 newtons. 454.74 newtons. So this is the amount of drag that is offered by the system when you are flying at this particular velocity in that particular trim condition. Okay. So you need to overcome this drag by producing so much thrust if you are using a jet engine. So if you want to use a propeller driven engine, then what we need to find out is power required. So can we quickly find out what is the power required for this condition? Right. So if it is a jet engine, yeah, we can talk in terms of thrust that need to be generated. So let us say if we employ a propeller driven engine, then we need to know what should be the power generated by the engine for this particular flight condition. So that means we need to figure out what is the power required by the system, which is drag or thrust required times the velocity of flight. So the drag is 454 or 455 newtons closely, which is 45 kg. This is the amount of force you need to produce in the forward direction of flight. So 0.7 newtons multiplied by 38.65. So this is approximately 17,734 watts. Right? This is the amount of power that you need to produce to make this system. Is it correct? 17,574. 574. Okay. Just check. So close to 17,574. Okay. Watts. So this is the amount of power that is required to propel the system forward if you are using a brushless motor. Propeller driven engine. Yeah. Okay. So we'll quickly solve another problem, another example problem. Or we'll give that as a assignment. No? Okay, so we'll end up this lecture. We'll give that problem as an assignment. Soon we'll be demonstrating that. No, do you remember? Can you recollect? So this neutral point. So let us say x and p bar is equals to x AC of wing, x bar AC or CL alpha of wing times x bar AC of wing, isn't it? Let's try to erase this part. So it is not connected with this question. So I am talking about a demonstration that we are going to take up. So CL alpha of wing times x AC of wing, eta ST upon S, CL alpha of tail 1 minus dou epsilon by dou alpha times x bar AC of tail, right, upon CL alpha of wing plus eta St upon S CL alpha of tail 1 minus dou epsilon upon rho alpha. Right? This is the definition of neutral point, right? Isn't it? From the definition we have derived this as the neutral point. So if we consider, see, this is about wing and tail combination. Right? Let us now consider a case we have identical wing and tail, same wing as tail. Okay. For example, if this is my wing, I will have this as a wing as well as tail separated by a adequate distance, right? Okay. What do you mean by that? I have same planform area. Okay. Am I correct? So I have same planform area for wing as well as tail. That means St upon S will be 1. Okay. So St upon S is 1. Further, I assume there is no downwash. No. Downwash effect is minimal. It is separated by very large distance. No. That means eta is 1 because half rho v prime square will be effectively half rho v square itself. And then this term disappears. This becomes 0. Right? Am I correct or not? So that means this becomes 1 and this term becomes 0. Okay? I am sorry. Yeah, not this one. That's epsilon term becomes 0. So, and lift of wing is nothing but lift of tail because we have two identical wings. So, in that case what happens is this is nothing but CL alpha of wing taken common out, x bar AC of wing plus x bar AC of tail. Why? Because CL alpha of tail is nothing but CL alpha of wing and the correction factor is 1 right now, isn't it? So there is no correction factor. I will take CL alpha of tail which is equals to CL alpha of wing common out of this numerator, and then what you have is twice that of CL alpha of wing, 2 times of CL alpha of wing. So this cancels out. What I have is x bar neutral point as the midpoint of the distance or the midpoint of separation of wing and x bar AC of tail upon 2. Am I correct or not? It is the midpoint. Can you see this? So this becomes, neutral point becomes the midpoint of these two. And we know if the CG is ahead of this neutral point, then we have CM alpha negative. That static margin is positive, CM alpha is negative. If it is behind the neutral point, CM alpha is positive, which means the aircraft behaves unstable. So we will try to demonstrate that, okay, in the next lecture. Thank you.